So good afternoon everyone, welcome back to multivariable control. For lecture today I'm going to finish the remaining part of the review on Laplace transform. So next you're gonna have practical work 1, Laplace transform for solving ordinary differential equations. But before you start the exercise, let me show the way how to solve differential equation using a conventional method. So when you have equation like this, you use characteristic equation. As you can see here, lambda plus 2 equals 0, then lambda equal to minus 2, which is real number. So the homogeneous solution has this form, constant e to the minus 2t. Okay? So this is just a review. I'm going to go quickly. For a particular solution, because the right hand side is just constant, 2 times step function. So u here actually it's a step function. Maybe it's to step. So it's right hand side is just like a constant. So particular solution should be constant, and you can see if it's constant, then the derivative of with respect to time equal to 0, which means 2y equal to 2. Then the particular solution is just 1. So y equal to 1. Then you have the total solution, which is the combination of homogeneous solution and particular solution. And by using the initial condition here, from here, then you can find the constant c, which is minus 1 in this case. And then you have the final solution like this. So you start from 0 here, and when time go to infinity, the curve just increase like this. It approaches to asymptote y equal to 1. Okay, so now you practice solve the equation by using Laplace transform manually. I can show you the idea of Laplace transform. You can see here. So from differential equation, you transform it into Laplace domain, okay, and then you make it as a canonical form like this. Then you just use table to see the Laplace inverse. Then you get the solution in the time domain, right? And here is the table, or the table of Laplace transform. Here. Once you have canonical form, for example, like this, or like this, then you can use Laplace inverse to get solution in the time domain. Okay. Too long, huh? Why so a lot of things like this? this one. Yeah, this one. Okay, so try to solve this. I just want to know how you remember about that transform. So first you use Laplace transform to get s y of s plus 2y of s equal to 2 over s. Okay. Then you get y of s equal to what? Here is the function. Okay, so you step like this. So the Laplace transform of step function Laplace transform of step function yeah, so Laplace transform of u step is just 1 over s. So from here you try to find y of s equal to what? Because you apply Laplace transform both sides, left hand side and also right hand side. So you have 2 over s plus 2, and then you make it into canonical form. You have this and you have this. maybe minus sign here. Okay. How you get the canonical form? Yeah, actually you just let's say just A like here and then B here, and then find a way to solve this equation to find A and B, right? So I'm not going to explain here because in control theory 1 I already explained in detail. So you're gonna find A equal to 1 and then you're gonna find B equal to minus 1, right? Then Laplace inverse of y of s would be one over s. Just go to check the table. So 1 over s is back to step function, and s plus a or s plus alpha, then you get this function, right? So here you get step of t minus e to the minus 2t u step of t. Then you have 1 minus e to the minus 2t times u step function. So you get exactly the same as this, right? Now for this practical work, okay, this is already done. Yeah, actually this one is just same thing. And then for the next point, here I want to show about the concept of transfer function. So transfer function means you have a rational function that you have numerator, both numerator and denominator are polynomial function. Okay. So just from our previous example here, actually 1 over s plus 2 is the transfer function itself, and 2 Laplace transform of this one become 2 over s. So 2 over s is from the input, right? Here 2 over s is from the input. So s plus 2 here, inverse of this is transfer function, right? Yeah, this one is from input, and 1 over s plus 2 is the transfer function. Okay. Okay. Let's see example 2. what is the transfer function for this equation or this system? Okay. Again, this u is step. Okay. You can clearly see that the transfer function is just inverse of the characteristic term, right? So from here you have, you do the Laplace transform, y double dot, you get s square ys, and then this term you get phi s, this term you get 6. Then the inverse of this term, this polynomial, is the transfer function. Okay, and the input here now is 6 us. Okay, the next point is the standard form of a transfer function for second order. Okay, so any second order system, we can rewrite the transfer function in this form. We have amplitude, we have natural frequency omega n square on the numerator, and we have this polynomial at the denominator. Okay, and this zeta is called damping ratio, omega n is called natural frequency. Okay, and then if we want to know the stability of the system, what do we do? If we want to know the stability of the system, let's say we have a transfer function representing dynamic of system. If you have input like impulse or step, then you get the output, and if the output converge, then you call the system stable, right? So to know the stability, by what you have is transfer function only. You don't see the output of the you don't see the outputs yet, and so how can you judge whether the system is stable or not?
I don't recall the exact formula, but I think it's the natural frequency squared needs to be superior to the ratio, something like that.
Can you repeat? I cannot hear.
If natural frequency squared is superior to I'm not sure.
So
I think it was the damping ratio. Then the will be locked because you stop at maybe
that's not the general key point, but in some case, for various. So actually, the stability we don't need to look at the natural frequency. We look at the root of the characteristic equation itself, or in the transfer function term we call poles. Poles mean roots of the denominator, right? So pole here mean roots of this term. And if you take this one and set it to 0, actually it is just, oops. Yeah, if you set this one to 0, which is this equation, and actually this is just characteristic equation. So if the poles or characteristic roots have positive real part, then system is unstable. If they have negative real part, okay, real part of S1 and S2 is negative, then the system is stable.
S1 and S2 are roots or
Yeah, S1 and S2 are the roots of this, and root and poles are equivalent. Root mean root of this equation. Poles mean the value S that make denominator 0. Okay.
So they say so 0 is the value for which the numerator is equal to 0. Because there was a term
root of this equation of the denominator, and not root of the transfer function itself, but root of the denominator, or you call it characteristic equation. So if let me make duplicate. I go next. Yeah. So here is the formulation of the poles S1 and S2. And you got delta prime of the polynomial equation like this. Then you can make judgment whether the system is stable or not just to look at the damping ratio. Ohn-GAN is always positive, okay? And damping ratio, if it is positive, then the system is stable because this real part become negative, right? Yeah. So now we only consider zeta greater than 0. In the case of zeta equal to 1, you have double roots. Then, and both of them are real number. And the system is stable and it's called critically damped, right? If zeta greater than 1, delta prime is positive, roots are real number, and we only consider stable systems, and in this case we call overdamped. Okay, overdamped. Damper is big, then it's overdamped. For zeta, for value of zeta from 0 to 1, then delta prime is negative, then roots are complex number, or poles are complex number, and in this case we call the system underdamped. Okay. And for the case underdamped, the formulation is like this. I think I made a little mistake here. Actually, if the original transfer function is like this, it has amplitude A here like this, then you should get A like this, right? Okay. So suppose A equal to 1, then when t go to infinity, because sigma is positive, what is sigma? Sigma is just this term, so which means this term. Okay, this is sigma. So if t go to infinity, this term die out, right? Becomes 0, which means while t approach to steady state, which is 1. And here is the curve representing all the cases. For this one, you see, when zeta equal to 1, this is critically damped. Yeah, this one is critically damped. Zeta equal to 1. Okay. And for the curve below that, zeta greater than 1, and we call it overdamp. Okay. And you see that the zeta equal to 0.9, 0.7, 0.5, 0.3. So the smaller the value zeta, the higher the overshoot. Okay. So this is called overshoot. You have any question? Okay. If no, then I go next. Okay, let's see the stability map according to the location of the poles S1 and S2 in the complex plan. So we say if the real part of if delta prime is positive, then S1 and S2 are the real number, all real number, and you need to check the sign to judge whether the system is stable or not. So the sign of all the real number, if is negative, then the system is stable. But in the case S1 and S2 are complex number, which means that delta prime is negative, which means that zeta less than 1. So complex numbers come from here, right? Come from here. So it's going to introduce a complex number here. Then the real part only this term, right? So if this real part is negative, then the system is stable. Okay. Negative mean on the left half plane here. So this is real axis, imaginary axis. So negative or real part means the whole set on the left half plane. Okay. So if location of S1 and S2 on the left half plane, then the system is stable. Otherwise, system is unstable. Right half plane, right? And S1 and S2 are always complex conjugate, 1 plus 1 minus. So if you map S1 and S2, if you put S1 here, S2 must be here. Or if S1 is here, then S2 must be here. Always complex conjugate. Yeah.
When you say that the system is unstable, this means that it will never come to constant value, it will always oscillate.
Unstable means it's explode. I mean, it increase, it diverge.
Okay.
Yeah. Like for example, you have inverted pendulum. Let's say you put it perfectly on the vertical like this. It seems stable, right? But to check whether it's stable or not, you just make impulse just a little bit. It's going to go away from this point, higher and higher. This means unstable. Theta increasing, right? You consider angle with respect of the pendulum with respect to vertical axis like this. So angle is increasing. That is unstable. If you have pendulums like just pointing downward pendulum like this, even you push it a little bit, it's going to come back here. So this system is stable. Okay, it converges to zero value, right? So here is the summary, the shape of the curve or the motion of the output. If you inject impulse response, impulse input to the system, this is gonna the behavior of the system. If you find the location of the poles. For example, here we just discussed earlier about stable system. Let's say the downward pendulum, okay, downward pendulum, even though you take initial value if you initially is 0, if you push it a little bit, it move up a little, but then it oscillates and finally it going to 0. Okay, so if the location of the pole is here, and of course there must be a conjugate here, right? This one and this one must be symmetric with respect to real axis, but in this graph the author does not show it. Okay, but always if you have complex number, you always have conjugate. And if on the left half plane but the root are real numbers, for example this one and this one, you have two root, right? This one and this one, then what is the curve? Okay, like this one. Okay, like this one, and it converge fast. See, it reach 0 very fast. Let's say this one of the root is here and then the one is just around here, let's say. Okay, and if the the most important is the smallest absolute value of the root. Okay, this one, because the big one just make exponential die out very fast. We don't need to count it. We don't need to account it. Just account the one that has absolute value smallest, right? And if the pole is around here, real number, but it's around here, then conversion not so fast, right? Because e to the minus sigma t, if sigma is large number, it means go to the left, right? Minus, it means go to the left. So this term die fast if sigma is big, right? When t go to infinity, this term die faster if sigma is bigger, something like that. Okay. Yeah. And then if you have purely complex number like this, and the conjugate one should be like here, then you have oscillation periodically. Okay, purely complex number. This is just the case of mass and spring. There's no damper. It's just very ideal case. In real life, you don't have this kind of thing, this kind of linear system. And if your poles are on the right half plane, you can see that in some case it might oscillate, but it grows faster, bigger and bigger, right? Yeah, let's say you have a feedback system, but your design controller not correct. Your controller is not the right one. You may make the system oscillate and with amplitude bigger and bigger over time, right? And okay, so if you got real poles, and yeah, both of them are real pole, then it's, the output is going to diverge like this. And if the value of the pole is small, it diverge not so fast. If the value is big, then it diverge even faster, right? Okay. So this is response from impulse, not response from step. Okay. So again, impulse, it means like you just push a little bit, just push and then stop pushing. Now let's see more detail on the behavior for second order system in the case of underdamped, right? When you have overshoot like this, it can go higher than the value of the asymptote here. So here, let's say it's called A final. Previously I used A instead of C, right? As long as this can go higher, it means it fall into the case under down. Okay. Is it slow? No, it's good. So we can see the detail or the richness of the property here. For example, overshoot denoted by OS like this or like this, and rising time it rise from 10% to 90%. Okay, so with this period is called rising time. You can see it rise from 10% to 90%. So rising time can be estimated like this, and then settling time at 2%. So this zone you can see here, it means from here to here just 2%. Okay, from here to here also 2%. It means this value divided by this value, I mean this 10 divided by this 10. So you can compute it as percentage, right? So 2% settling time is like this, right? All like this. Why different? In this case, if you consider zeta between 0 to 0.9, so settling time just 4 times of 1 over sigma. Yeah, I call this sigma. But if you consider any value of zeta, I mean even it very very close to 1, then settling time maybe a little bit bigger, just something like that. So it's just different approximation. Okay. Actually, it does not. It's not a big deal. For the estimation of settling time, you just need to know the rough. Usually, some system is very fast. So whether it's the settling time is 0.1 second or 0.2 second, maybe it doesn't matter, right? Yeah.
How do we determine sigma or TS?
Sigma. Yeah, sigma is zeta times omega n. Yeah. Yeah, sigma here, just this term. Oh, I think I made a mistake here as well. Divide like this, so it's better to correct it now, otherwise I forget. Okay. And then oops. This one. Okay, so for this one, just to explain, if the location of poles shift by in a certain route or a certain way, let's say in the case 1, the pole is here and its conjugate is here, then you have the curve like number 1 here, like this one. If the location of pole shift or parallel to the vertical axis, it means the real number is still the same, right? But the imaginary number increase. How does this imply? Because the real number is same, the term exponential minus sigma t is still the same, right? So the decay term, the decay amplitude is still the same. You can see? Okay. And because complex number increase, it means oscillation is more often. Frequency is higher. So the shape is going to be like this. Okay, like you can see number 3, you see that oscillation is more often and overshoot can go higher. Okay, but cannot higher than the envelope of the decay exponential here. And the second case, if the complex number is still the same for case 1 and case 2, but the real number increase from here to here, so it means that the decay for the case 1, decay is like this. The number 2, the decay even faster, right? So that's why number 2, you can see that overshoot is not so high, like that. How about this one? For this one, if the location of poles in the case 2 and 3 in such a way that it's arranged that like a line from 0 to here, and with the angle theta of the ratio of, like, okay, sorry, I mean well, as long as this arrangement across the row like this, so it means theta is fixed, right? Theta maybe you can consider with respect to x-axis. Here theta is fixed, right? Case 1, case 2, case 3, theta is fixed. And if you calculate tangent theta, which is the ratio between complex term and real term, then you can see that it is a function of damping ratio only. So it means if damping ratio is fixed, omega m can be different for case 1, 2, 3. You still have the same overshoot, because overshoot also in function of damping ratio only, right? This is what it means. Okay. Do you have any question? No?
On the previous slide, why the rising time is from 10% to 90%?
It's just terminology. Terminology means like people in the control society just consider, okay, 10% because second order, it has like a inflection point. No, inflection point. It goes very slowly first, and then it starts rise very fast before it converges, right? So it seems the rising at the highest speed is in between 10% to 90%. So it's just terminology, right? Okay, so before you take a break, I'm going to explain this briefly about block diagram. Okay, so let's say you have a dynamic system. Okay, so you have system that can be modeled as a dynamical equation, namely differential equation, right? You can derive it as ODE, and then you take Laplace transform of the ODE to find the ratio between output and input. Then you get the transfer function GOS, right? This one, plan from dynamic system. So here is input, and here is output. And in this case, let's say you use a sensor to measure the output, and your sensor could be a dynamic system as well, right? For example, if your sensor involves spring, let's say for electrical system, maybe the sensor has inductor, capacitor, right, a resistor, and then it's also dynamic system. And okay, so block diagram here is just, well, in some case you need feedback. Okay, some case you need the control, feedback control like this. Then you find the transfer function from the reference to the output here. So this is, let's call this one as a G feedback. Okay, GF, let's call it GF. So this is GF. Okay, input as a reference and then output as YS. Okay, and this is the formulation. So how you can find this? Actually, it's not difficult. You just denote error of S here, error here. You can have error of S equal to RS minus, because here you have Y here, and then Y times this one, you have H times Y, right? So you have A of S times Y of S, right? And another one, you have a relationship between ES and Y of S. So you have Y of S equal to E of S times G of S, right? Then you just substitute Y in here, and you manipulate, or maybe you substitute E of S. You find E of S from here. Okay, let's say you have E of S equal to Y divided by G, right? Y of S divided by G of S. Okay, so you substitute in here, you can find this. It's not difficult, right? So just G of S over 1 plus this times this. Okay, so take a break about 5 minutes before we continue to practice 2.